Hello students, till the time in this chapter structure of atom, what we have dealt about atom, that is according to the modern atomic theory of atom. But now in this segment we will be dealing about those initial efforts that led to be resultant in the modern atomic theory. So now in this segment we will be dealing with the starting efforts that I am going to term as history of atom. Now, if I talk about the very initial idea that was given for this atom, then this very starting idea was given by an Indian sage named Maharshi Kannad. Maharshi Kannad was the first one who said this, that whether all kinds of matter, whether the given matter is in solid state, liquid state or in gaseous state, these all matter are made up of one fundamental unit, and this fundamental unit was termed as Parmanu by Maharshi Kannad. This Parmanu is the Hindi translation for this word atom, and since Maharshi Kannad was an Indian sage, so he named this fundamental unit in the Hindi language as Parmanu. According to Maharshi Kannad, he named this matter as Padarth. So the idea of Maharshi Kannad was that all kind of Padarth are made up of only one fundamental unit, and this fundamental unit was termed as Parmanu. Later on, a different Greek scientist came in the history, and the name was Democritus. Democritus supported the idea of Maharshi Kannad, and he also suggested this thing, that all kind of matter, they are made up of one small indivisible unit which cannot be further subdivided, and since he was a Greek scientist, so he named this small indivisible unit in his Greek language, and for this small indivisible unit he used the word atmos. Since in the Greek language the atmos word, it has the meaning non-cuttable, or this word can be used for indivisible. So this was the Democritus and Maharshi Kannad, and they both gave the same idea that all the matter are made up of a small indivisible unit. But till the time, what the idea they have supported, that was according to their theoretical explanation, and there was no any clue to prove these kinds of ideas. So as they proposed their ideas, there was not so much attention on these ideas, since there was there was no any experiment to prove these initial ideas. So later on in the history, now we will be dealing about those experiments that were the very starting one, and who suggested that the idea proposed by Maharshi Kannad and Democritus was correct. And these experiments were done by Lavoisier, and the another scientist was Proust. Lavoisier and Proust, they did some experiments in the laboratory, and on the basis of the result of those experiments, they proposed some laws. These laws are known as laws of chemical combination. Basically, this law of chemical combination is a group of 5 laws. Initial 2 were proposed by Lavoisier and Proust. So now we will be dealing about only those laws which are proposed by these. And the very first law is the law of chemical combination, and the very first law is law of conservation of mass. This law of conservation of mass was proposed by Lavoisier in the year of 1774. Lavoisier was doing some experiments in his laboratory, and while doing these experiments, he found that always the mass of product was equal to the mass of reactant. Such as, if I start with a molecule calcium carbonate, and if I heat this molecule of calcium carbonate, so by the heating process, this reactant will convert into a new substance that can be termed as product. And here the products are a molecule of calcium oxide with a molecule of carbon dioxide. Now, if I start with 100 gram of calcium carbonate, then surprisingly, Lavoisier found this, that the total mass of product was also equal to this, and the mass of product was 100 gram. Again to prove this, that whether the given result is true in all the cases or not, he changed the mass of reactant. And now if I start with the mass of reactant as 200 gram, again the mass of product was 200 gram. If I take the mass of reactant half as compared to the initial one, and if I start with 50 gram of calcium carbonate, again the mass of product was found as 50 gram. So and when he changed the reactant again to prove this result, and now in this time if I start with the molecule of hydrogen and oxygen to form the molecule of water. Now if as the starting mass of reactant I take 18 gram of this reactant, in this 18 gram 2 gram of hydrogen gas is going to react with 16 gram of oxygen. Then if I take 18 gram of reactant, according to this law, the final mass of product will be again 18 gram. Now if I change the mass of this reactant, and as this if I start with 36 gram of reactant, I will be finding the mass of product is again 36 gram. So as he was founding the same kind of results in all kind of experiments, and by changing the reactant nature or the mass of reactant, the results are not going to be affected. So finally he stated this result in the form of law, and according to the law, the mass of reactant is always equal to the mass of product for a chemical reaction. And this statement is termed as a law which is known as law of conservation of mass. According to the law, if I say that a mass of reactant will totally convert into the mass of product, means a mass cannot be destroyed in any form or it cannot be created, then this is known as the conservation law of mass. So the law is mass can neither be created nor be destroyed in a chemical reaction. And the statement what I have written just now, this statement is known as the statement of law of conservation of mass, which was proposed by Lavoisier. Now this law is useful to solve many kind of numerical problems, such as if I talk about a numerical where this sodium carbonate NaHCO3 is going to react with sulfuric acid H2SO4, and by the reaction of this metallic bicarbonate with acid, always a fixed products are formed, and the products are salt Na2SO4 with a molecule of carbon dioxide and water. If I am to apply the law of conservation of mass, so I am to take the balanced chemical reaction of this, that is like 2 molecules of water and finally 2 molecules of carbon dioxide molecule will be formed. Now if as the starting mass of reactant, if I start with 168 gram of sodium carbonate and the given mass of sulfuric acid is 98 gram. Now finally they have given us that the mass of carbon dioxide molecule formed is 88 gram and the water molecules are going to be formed as 36 gram of water. Now in this reaction, if they are going to ask that what will be the mass of this formed Na2SO4, so we can calculate this mass of product with the help of law of conservation of mass. Now just now we have read that the mass of reactant is always equal to the mass of product when they are going to react completely. Then if I apply this relation for this equation, then I will be finding that the mass of reactant is 168 gram plus 98 gram. Now it should be equal to the mass of product, that is mass of Na2SO4, that's unknown, so I have taken it X. The mass of carbon dioxide 88 gram plus mass of water molecule, that is 36 gram. From this equation, if I go to calculate the value of X, so here I will be getting that total 260 gram of reactants are going to react and they are going to form the mass of product, that is X plus the mass of left two reactants, and the sum is 124 gram. Now from here if I collect the value of X, the value will be 142 gram. So this equation or this relation can be used to solve many kind of numerical problems, such as the one example is like this. Now this was for the mass of law of conservation of mass, but as such I have stated that this law is valid only for chemical reaction. If I talk about nuclear reaction, so there this law is not applicable. Because in the nuclear reaction, if I talk about the reactant, so these reactants are going to convert into product plus a fixed amount of energy is released there. So the total mass of reactant, it is utilized in two forms. One half, some part is going to convert in form of product and some part of this is going to convert in form of energy. So here the mass of reactant, it will always be greater as compared to the mass of product, and the law of conservation of mass, which was going to say that the mass of reactant is equals to the mass of product, that is not true here. So that the law of conservation of mass, it is true only for the chemical reaction, and nuclear reaction they are taking as the exception of this law of conservation of mass. Now if I deal with the second law, which gave the basic for the practical theory for this atom, and this law was proposed by Proust, and the name of law is law of constant proportion. Now, as I said initially that these two laws are totally based on the results what they got while doing the experiments, and there is no theoretical explanation for these laws were given by Proust and Lavoisier. As if I talk about this law, so for the starting I am going to prove this law for the molecule of carbon dioxide. According to the law, if I take the pure sample of carbon dioxide, then irregarding of the nature of source, the ratio of carbon and oxygen in these different kind of samples which contain pure molecule of carbon dioxide will be always same. And if I find the value of this ratio, then as we can see that in this molecule only one atom of carbon is there and the mass of one atom of carbon is 12. If I talk about carbon dioxide molecules, so here two oxygen atoms are there and the total mass of oxygen atoms in carbon dioxide molecule is 32 gram. Now if I compare the ratio for this, then the ratio will be 3:8. Then according to this law, if the pure sample of carbon dioxide is taken, then always the ratio should be 3:8. Such as if I prove this law by taking the different samples of carbon dioxide, and as the starting sample I am going to heat the molecule of calcium carbonate. As we know that by heating this molecule of marble or calcium carbonate, it forms calcium oxide and carbon dioxide gas. This carbon dioxide gas is working as a sample first here. Now if I am to take the another sample of carbon dioxide, so I can react the carbon with the environment oxygen gas, and by the burning of carbon in the presence of oxygen, it will convert into carbon dioxide molecule that can be termed as sample 2. The third sample of carbon dioxide can be collected from the environment. Since the environment contains 0.03% of carbon, so this carbon dioxide, pure carbon dioxide, will work as sample 3. As Proust found the ratio of carbon and oxygen for these three pure samples, he found that the ratio is 3:8 always. And this ratio doesn't depend on this, that what is the nature of carbon dioxide or what is the source of this carbon dioxide from where you have collected this. So finally he concluded this result in a form of law, and this law is known as law of constant proportion, since the ratio or proportion of elements in a pure compound is always constant. So this law is known as law of constant proportion. This law was proposed by scientist Proust, and the year was 1799, and the statement of this law is, in a pure sample of compound, the ratio of constituent elements will always remain same irregarding of the nature of source. So that is the law of constant proportion. Now we will be dealing about those examples where this law is not applicable. As such, we have read that the law of conservation of mass is not applicable for the nuclear reaction. Same here, if I talk about the molecules which are formed by the isotopic elements, then the molecule which are formed by the isotopes will not follow this law. Such as if I take the molecule of carbon dioxide, then as we know that carbon, it exists in three isotopic forms. The one isotope form has the mass number 12, the second one has mass number 13, and the third one has mass number 14. If I try to form this carbon dioxide by the reaction of carbon and oxygen, then in the case if here the carbon atom has the mass number 12, and another, if I form this carbon dioxide by the reaction of carbon and oxygen, and here the carbon is like that with the mass number of 14. Now in this case, if I find the ratio of these two pure samples of carbon dioxide, then here in the first one the mass of carbon is 12 with the mass of oxygen, that is 32. In the second one the mass of carbon is 14 and the mass of oxygen is 32. If I find the ratio of the first pure sample, the ratio is 3:8, while the second one, that is also the pure sample of carbon dioxide, here the ratio is 7:12. So we can see here that these two are the pure sample of carbon dioxide, but the ratio of atoms, due to the presence of isotopes, the ratio is not going to be same. So that is the exception or the limitation of law of constant proportion, that in case of isotopes the ratio for two pure samples will not be same. It depends on the mass of isotope what is going to participate in the formation of molecule. That is about the law of constant proportion. Now we are to move to the further efforts which were done in the field of modern atomic theory of atom. So as I have said that these two laws, they were the first practical, they gave the first practical base for the modern atomic theory, but there was no any theoretical explanation for these two laws. Now to explain the result of these two laws theoretically, Dalton came in the history and he proposed his theory that is known as Dalton's atomic theory. John Dalton was an English school teacher, and on the basis of the initial idea, he tried to explain the term atom more. And these postulates which were given by Dalton, they are collectively known as Dalton's atomic theory. So now we will be dealing about the points or the postulates of Dalton's atomic theory one by one. And the very first postulate of Dalton's atomic theory is, he stated the same thing what was given by Democritus and Maharshi Kanad, and according to him, all the matter, they are made up of only one fundamental unit, that is known as atom. This atom word which is related with the English language was first given by John Dalton, and according to him, this atom is the smallest indivisible particle of a matter which cannot be further subdivided. So that is the first postulate of this Dalton's atomic theory, and he defined the atom as the smallest indivisible particle. Now, if I try to explain this atom more, and if I compare the atoms of one element, then according to Dalton, those atoms which belong from only one element, as we know that this element is a collection of atoms. If I compare the two atoms which are related with a single element, then according to John Dalton, these two atoms which are related to a single element, if I compare the properties of these two, the properties will be same in each and every regard, whether I go to compare their mass, their chemical properties, their size or their density. They will be same in each and every regard, and that is known as second postulate of Dalton's atomic theory. So the second one is, the atoms of one element Now, if I compare the atoms of two different elements, such as if I have the element one is named as E1 and the second element I am going to name as E2. Then if I compare the atoms of these two elements which are going to termed as A1 and A2, then according to Dalton, these two atoms they will be different in each and every regard, and no any two properties will resemble in each two. And that is the third postulate that can be said as the atoms of an element are different from the atoms of another one. For example, if I take the element iron and compare the atoms of iron with the atoms of carbon, then we will not be finding any similar property between these two atoms, and they will be different in each of their properties according to John Dalton. That's the third postulate of Dalton's atomic theory. Now we will be moving to the fourth postulate of Dalton's atomic theory, and according to this postulate, the atom can neither be created nor be destroyed. Such as if in a chemical reaction or if in a process I start with one atom of calcium, one atom of carbon and three atoms of oxygen, then according to John Dalton, the number will always remain same, and it is not possible that by this one atom of calcium you can form two atoms of calcium. If I have started with one atom of calcium, so finally I will be getting only one atom of calcium. If I have started with one atom of carbon, so it will be resulted in one atom of carbon, and if in the starting I have taken three atoms of oxygen, so finally I will be getting three atoms of oxygen. This number or their nature cannot be changed, since the atoms can neither be created nor be destroyed. And that is the postulate of Dalton's atomic theory, which will help us to prove the law of conservation of mass. Such as we have read initially, that this law of conservation of mass which was proposed by Lavoisier, this was not having any theoretical explanation. Lavoisier said this, that if I start with 100 gram of calcium carbonate, I will be getting the mass of product that is equal to 100 gram, but why it's going on, it was not explained by Lavoisier. Now we can explain this law according to this postulate of Dalton's atomic theory. Such as if I take that I have started with 100 gram of calcium carbonate, then this 100 gram is due to the presence of one atom of calcium which is going to contribute 40 gram in this molecular mass. In this molecule of calcium carbonate, one atom of carbon and three atoms of oxygen are there, which are going to contribute 12 gram and 48 gram respectively. Now if I take the sum of this, I will be finding that the total mass contributed by these atoms is 100 gram, and this total mass of reactant is due to the presence of these atoms. Now according to John Dalton, if I have started with this kind of condition where one atom of calcium, one atom of carbon and three atoms of oxygen are there, so finally the condition will be remaining same, and finally I will be getting one atom of calcium, one of carbon and three atoms of oxygen. If the number is going to be same, so the mass contribution by them will be always same, and the mass contributed by them is 14 gram, 12 gram and 48 gram respectively, which will result in the total mass of product that is 100 gram. So this postulate can be used to prove the law of conservation of mass. And now finally we will be moving to the final postulate of Dalton's atomic theory, that says that whenever these atoms combine, these always combine in a fixed ratio by their mass, and the ratio by mass their ratio by mass is always a simple ratio. So that's the next postulate, and that statement is a compound is formed by the combination of atoms and the combination will be always in a simple ratio by their mass. So by the combination of two or more atoms in simple ratio by their mass. Such as, if I talk about the molecule of carbon dioxide, then according to John Dalton, the ratio whenever this carbon and oxygen will go to combine the molecule of carbon dioxide, the ratio will be always a simple whole number ratio, and as we have proved that here the ratio is 3:8. So this is the final and the fifth postulate of Dalton's atomic theory, and this postulate helps us to prove the results of law of constant proportion. As we have read initially that according to Proust, if I have started with a pure sample of carbon dioxide, then the ratio of carbon and oxygen was here again were here always 3:8. So why it was there? It was not explained by Proust, but now we can explain this. According to Dalton, whenever these two atoms will combine to form the molecule of carbon dioxide, the combination will be always in a fixed simple ratio, and the ratio is 3:8. So the converse of this is the law of constant proportion that can be proved with the help of this statement. Now we will be moving to the merits and the demerits of Dalton's atomic theory. The very first I am going to talk about the merits of Dalton's atomic theory. Dalton's atomic theory is the milestone in the history of this discovery of atom, and it has helped us in many ways, and the some merits of this Dalton's atomic theory are as such. The Dalton's atomic theory is the first one who defined the atom as the smallest unit which participates in a chemical reaction. So the very first statement that is true for the Dalton's atomic theory is Dalton defined atom as the smallest unit which participates in a chemical reaction. And as we have started with this structure of atom with the definition of atom, so we all know that this statement is true till now. Basically, if I go for the further division of atom, so there are valence electron which basically participates in a chemical reaction. But since they do not exist independently, or they do not show all the properties of elements, so we can take this atom as a fundamental unit which is going to participate in a chemical reaction, and that is the first merit of Dalton's atomic theory. Now if I talk about the second and the very most important contribution of this Dalton's atomic theory is that this theory, it gives a theoretical explanation for two laws of chemical combination, and these laws are law of conservation of mass, and the second law which can be explained on the basis of this Dalton's atomic theory is law of constant proportion, which is proposed by Proust. So these are the two important merits of Dalton's atomic theory. Now we will be moving to some disadvantage or demerits of Dalton's atomic theory. If I talk about the very first postulate of Dalton's atomic theory, then in his postulate he stated that all the matter are made up of one smallest indivisible unit that is defined as atom. But now we know that this atom is not the smallest indivisible unit of any matter. This atom can be further divided in three fundamental subunits that are known as electrons, protons and neutrons. So as he stated the atom as the smallest indivisible unit, this statement is false, and that can be counted as a demerit of Dalton's atomic theory. So the statement is the atom is no longer supposed to be indivisible. The next demerit of Dalton's atomic theory is based on its second postulate. In his second postulate he stated that all the atoms which are present or which are related with an element, they will be same in each and every regard, and there will be no any difference in their properties. But now we find that the isotopes, they do not follow this postulate. Such as if I take the element of chlorine, then this element of chlorine can contain two kind of atoms, one with a mass number of 35 and second with a mass number of 37. Here, these two atoms, they are related to a single element, but their mass number is different. And according to John Dalton, they should be same in each and every regard. So here, the isotopes are not going to follow these properties, and these isotopes cannot be explained on the basis of Dalton's atomic theory. The next and the final demerit of this Dalton's atomic theory is it cannot explain the presence of isobars. As we know, or as we have read initially, that there may be one kind of similarity between the atoms of two different elements, such as if I take the element of argon and compare this with the atom of calcium, then they are having the different chemical properties, different size or different density, but the one similarity between these two is the mass number for these two is 40, that is the same value. So if I compare the atoms of two different elements, they may be same sometimes, and these two atoms with the same value of mass number are termed as isobars. So these isobars cannot be explained according to Dalton's atomic theory, because according to Dalton, there may not be any kind of similarities between the atoms of two different elements. So again, the final one is isobars cannot be explained according to the Dalton's atomic theory. And that is about the history of this atom. Now further we will be dealing after this.